welcome to Chapter 9, Part 2. So last time in Chapter 9 we left off, we talked about ionic bonding and lattice energy and the Born-Haber cycle and lots of different topics related to ionic bonding. And so in this lecture, we are going to switch gears and we are going to talk about covalent bonding. So those are the bonds formed between two nonmetals that share their electrons. So that's going to be the focus of this lecture, along with drawing Lewis structures. So covalent bonds are formed between two nonmetal atoms, and these nonmetal atoms are sharing electrons. So this is different from ionic bonds, where we're seeing that transfer of electrons. The electrons go from the metal to the nonmetal. In covalent bonds, we're not seeing that transfer of electrons. Instead, they are sharing the electrons in order to get to 8 valence electrons. So here on this slide, I have a bunch of different bonding models for methane. This is probably the closest one to what we're going to use in this class. We would put, carbon at the middle, and then we would draw the hydrogen bonds. This is kind of how it's shown in organic chemistry. This is a 3D structure here. This one, where it's got the wedge is shown coming out of the page, kind of towards you, and this dashed is shown going into the page away from you. So that's like a 3D model. And then we have these other ones. This one's called a space filling model, and then this one's called a ball and stick model. We're not going to really get into these, but there are lots of different ways to show these covalent bonds that are formed. And as you go farther into chemistry, you'll get more and more practice with all these different types. So covalent bonds are sharing electrons in order to obtain an octet. And so we talked about octets last time. And octets are where an atom will have 8 valence electrons. So that's kind of the name of the game, right? Everyone's trying to get to 8. So that's when we talk about octets, that's what we're talking about. So these atoms are bonded together in order to form molecules. So when we have 2 or more atoms bonded together, we call it molecules. And this is from a very, very strong attraction. So covalent bonds form molecules, or molecules are formed through covalent bonds. That's not what we use, this term molecules. We don't use that for ionic compounds, just for covalent. And so the within the molecule, those atoms are being bonded by a very, very strong attraction. So like if we were to think about methane, which was on the last slide, this guy, CH4, these carbon-hydrogen bonds are very, very strong. So that's when it's talking about a strong attraction. It's talking about these like carbon-hydrogen bonds within a molecule. But the molecules are generally weakly attracted to each other. So that would be like if we had another methane. Here, we're saying, okay, the attraction between these molecules is fairly weak, and that's something that's different between ionic and covalent compounds. So molecules within them, very, very strong, like the bonds, but generally between them are pretty weak. And so this gives us physical properties like they have lower melting and boiling points than ionic compounds, because ionic compounds are formed by that alternating pattern of, positives and negatives. And so those are very strong attractions, which lead to high melting points and high boiling points. But since there's a weak attraction between molecules of covalent compounds, we get lower melting points, lower boiling points. So, Octet rule. Combinations of elements tend to form so that each atom, by sharing electrons, has an octet of electrons in its highest occupied energy level. So we're all trying to get to 8. So this is monatomic chlorine, just chlorine, floating around by itself, which we know doesn't happen, right? We remember Hofbrinkel. And if we think about Hofbrinkel, we remember that chlorine is a diatomic. And the reason that chlorine is a diatomic is that when it floats around as diatomic chlorine, these electrons in the middle are being shared by each of the 2 chlorines. So like, if we had another one, right, and we did this, each one has 7, but they can share these ones in the middle so that they have 8, and they will form a bond here. Okay, so then when we count, like this chlorine has 1, 2, 3, 4, 5, 6, 7, 8, and this chlorine has 1, 2, 3, 4, 5, 6, 7, 8. So they each have 8 now by sharing those electrons in the middle. And so those electrons in the middle are bonding pairs, right? These ones in the middle, or bonding electrons. And then all of the other ones that are not participating in bonding, like, let's say these, we call them lone pairs. So how do we draw Lewis structures? So Lewis structures show how valence electrons are arranged among atoms in a molecule. So this is carbon tetrachloride, CCl4, and we have carbon in the middle here, and then we have the 4 chlorines around the outside. Each bond, like this, represents 2 electrons. So if we were going to go through and count, the electrons surrounding each one of these atoms would be 8. Like carbon has 4 bonds going to it, so 2, 4, 6, 8. And then each of the chlorines has 8 because they're each, they have 6 lone electrons, 3 different lone pairs, and then they're each getting one of the bonds to get a total of 8 valence electrons. But the Lewis structures show the arrangement of these electrons around the atoms. Lewis structures reflect the central idea that the stability of a compound relates to the noble gas electron configuration. Again, that means we're all trying to have 8 valence electrons. Shared electron pairs can be represented by 2 dots, like I was showing you on the previous slide, or by a single line. Typically, showing them with 2 dots is more kind of an elementary thing. When you're you're starting out drawing Lewis structures, you might use the dots. So you're going to want to shift over to the lines if you've been doing dots before. But the dots can help you on your way to the lines. Just a note, though. Okay, so these ones, the ones on the outside, right, the lone pairs, do not ever make those align. I know there's 2 electrons, but they're not bonded to anything. They belong to the chlorine, and so we show them as dots. So I've seen some people do like this. Don't do that. Don't do any of that. All right, electrons that are shared by atoms, we call those bonding pairs, like I said. And then electrons that are not shared by atoms, but that belong to a particular atom, are called lone pairs. Sometimes you'll hear them called non-bonding pairs, but just in general in chemistry, we typically call them lone pairs. So, bonding electrons can be displayed as a dashed line, right? So here on the left, right, in ammonia and in methane, it's showing the bonding pairs as these dots. And like I said, that's kind of like a newbie thing. Like when you're first, drawing Lewis structures, you might show them that way. But whenever you have the 2 electrons between the atoms to show them bonded, please draw them as lines. It's a good habit to get into. And then the non-bonding electrons, though, they have to be displayed as dots. So you can't connect the dots of those, nitrogen lone pair up there. So bonding electrons, show them as lines. Non-bonding electrons will show them as dots. So a couple things about the octet rule. So the second row elements like carbon, nitrogen, oxygen, and fluorine must observe the octet rule. They also observe this thing called the HONC Rule, which is kind of a rule of thumb, which we'll get to on the next slide, but they must observe the octet rule. They cannot break it. They must have 8 valence electrons. The second row elements, boron and beryllium, often have fewer than 8 electrons around them, and for this reason, they are really, really reactive. Boron will often have 6 valence electrons, and beryllium will often have 4 valence electrons. So these 2 elements don't need to have an octet. They can have 6 or 4, respectively, which is why they are super, super reactive. Elements in the third row and anything below that can exceed the octet rule. They actually can have more than 8 valence electrons, and this is by accessing these empty d orbitals, right? So we know that the d block starts, with 3d, which is why anything in the third row can access those 3d orbitals. More on that later, though, when we start actually breaking these this octet rule. So if you've, gone through chemistry and they've told you the hard and fast rule where, things cannot have more than 8, well, they can, But we're going to try and satisfy these octets first. If you can make a Lewis structure and obey the octet rule, do that. If the only way to draw the Lewis structure is by breaking the octet rule, then we'll place some electrons around elements that have, these available d orbitals. But more on that later. So the HONC rule, if you've never heard of the HONC rule, it's just kind of a rule of thumb. It's, if you've never heard of it before, that's okay. But it's like I said, it's just kind of a way to make drawing Lewis structures a little bit easier. So hydrogen and the halogens, so things that start with H, right? Hydrogen, halogens, typically form one covalent bond. Oxygen and sulfur and, things below that will typically form two covalent bonds. They can form, a double bond or two single bonds, but a total of two bonds. Nitrogen and phosphorus and things below that form three covalent bonds. So you can have a triple bond, you can have three single bonds, or you can have a couple combinations. You can have a double bond and single bond and things like that. And then carbon and silicon and everything below that form four covalent bonds. So you could have two double bonds, you could have four single bonds, you could have a triple and a single, double and two singles, right? But so this HONC rule is just, 1, 2, 3, 4, the number of bonds that these elements typically make. So that's what the HONC rule is. If you've never heard of that, then, you can use it if you think it's handy. If not, that's okay too. So let's try and draw a Lewis structure. So this is CH3Cl. So the way that we do this is we want the atom that can make the most bonds in the middle. So if we think about the HONC rule, right, we have hydrogen and halogens, right? So chlorine is a halogen, and then we have hydrogen. So all of these, hydrogen and chlorine, they can only make one bond, whereas carbon can make four bonds, right? HONC, 1, 2, 3, 4. So carbon can make four bonds, so we're going to stick carbon in the middle of our structure. Carbon goes in the middle of a lot of structures, just in general. And then we are going to figure out how many valence electrons we have to use. Oh, there we go. So how many valence electrons do we have? So carbon has 4 valence electrons. Each of the hydrogens comes with 1, right? And there are 3 of them. And chlorine comes with 7, so total 4, right? 4 plus 3 plus 7 gets us 14. So we have 14 electrons to use in our structure. This is going to be kind of straightforward when we're doing these, these first couple examples. As you get into bigger and bigger structures, counting up the total number of electrons that you have to use becomes very, very important. Okay? So our first step in using up electrons is to join the peripheral atoms to the central atoms with electron pairs. So that means join all of the ones on the outside to the middle ones, right, by using some electrons. So here they go. Again, I'm going to start with these dots. I'll replace them later with lines, though, just starting from the beginning. So we've joined our peripheral atoms to the central atom with electron pairs. Then we are going to complete octets on the atoms other than hydrogen with the remaining electrons. The reason, right, that it's other than hydrogen, follows the duet rule, right? So hydrogen only ever wants 2 electrons. So like this hydrogen has 2, this hydrogen has 2, this hydrogen has 2, hydrogen's done. Hydrogen can only form 1 bond ever. And when we're going around and checking octets to make sure that your structure looks good, you don't really need to check on hydrogen. As long as hydrogen has only made 1 bond, you're done. The carbon in the middle right now has 2, 4, 6, 8 electrons around the carbon. So the carbon's done. Carbon has followed the octet, but this chlorine over here, chlorine right now only has these 2 valence electrons that it's sharing with carbon. So far in our structure, we have used, right, 2, 4, 6, 8 to connect the peripheral atoms to the central atom. So we've used up 8. So we have 6 left that we need to put on our structure. And in this one, they are all going to go to this chlorine so that chlorine can have 8 valence electrons. So now when you go around and check, make sure everybody's got 8, hydrogen's only got 2. This looks like a really solid structure. There we go, they're going to fly in. All right, so fluorine. Fluorine, we know, is a diatomic molecule, right? We were talking about Hofbrinkel. Right now, each fluorine has 7 valence electrons. So the reason that fluorine doesn't just, float around as, fluorine by itself is because that would be unstable. It only has 7 valence electrons. In order to form a stable molecule, it will bond with another fluorine. So each fluorine brings 7 valence electrons to the table, and they share these 2 in the middle so that they each have 8. So that bond between the fluorines is a single bond. So this is when 2 atoms share 1 pair of electrons. And in that one, pair of electrons, there are just 2 electrons, right? So we just made essentially, one line. So there we are. So as the fluorines come closer and closer together, right, they form this overlap, right, where they can share these 2 electrons, and we'll draw that as a line between the 2 fluorine atoms. But again, we're always still going to show these lone pairs that are out there. Atoms may have more than one single bond if they need to complete their octets, kind of like we saw in the previous example, right, where carbon needed to have, those 4 single bonds in order to complete its octet. So here's oxygen. Oxygen is also a diatomic molecule. And so it doesn't, again, just float around as O by itself, but it floats around as O2. But what's happening here is that each oxygen has 6 valence electrons. So let's say that they were like, if they were like the fluorines, here's my oxygen with 6 and my other oxygen with 6. If they just shared these electrons, then each one would have 7 valence electrons. And so they can't get away with just sharing those 2 electrons. They will share 2 pairs of electrons like this. So they'll share these electrons and these electrons. And so this sharing of that many electrons, this is called a double bond, where each atom is sharing 2 electrons with the other atom. Okay, so but again, if we went around and counted, right now each oxygen has 8. 1, 2, 3, 4, 5, 6, 7, 8 on the left oxygen, and 1, 2, 3, 4, 5, 6, 7, 8 on the right oxygen. So each oxygen gets an octet because of these double bonds, right? That sharing of 4 valence electrons, right? 2 pairs of electrons, the 4 electrons, is called a double bond. And so the way that we'll draw this, rather than how you saw it with all the stacked or, with like this mess, we show this as 2 single lines between the oxygen atoms. These double bonds are shorter and stronger than single bonds. Because there are more electrons that are being shared between these 2 atoms, it's a stronger attraction to the nuclei between the 2 atoms. So that draws both of the oxygens in closer and makes it stronger and shorter than a single bond. So we call this an increase in multiplicity. So if you see that term, that's what I'm talking about. Instead of having 1 bond between the atoms, now there are 2 bonds. And so, having a double bond is a shorter and stronger bond than a single bond. So here's nitrogen. Nitrogen is also a member of Hofbrinkel, right? And so now each nitrogen has only 5 valence electrons. So in order to get to 8, it's going to share 3. Each nitrogen will share 3 of its electrons, so that there are 6 electrons total being shared between these 2 nitrogen atoms. And so we call this a triple bond. So 2 atoms that are sharing 3 pairs of electrons, or 6 electrons total, looks like this, right? So, as the nitrogens get closer, they share 6 electrons. So rather than drawing it like that, we draw 3 straight lines between the nitrogen atoms. That is a triple bond. And again, that is even stronger and shorter than the double bond, which again was shorter and stronger than the single bond. The triple bond will be the shortest and strongest of them all. You cannot make quadruple bonds. So if you ever see that, somebody is like pranking you, or it's a trick question or something like that. But triple bonds are the strongest and shortest. So let's try one. Draw the Lewis structure for carbon dioxide. So first thing we need to figure out, how many electrons do we have to play with? We have 16 electrons total, right? We have 4 from the carbon, and then, right, so this is carbon plus 2 times, the oxygens, and each oxygen has 6 valence electrons. So we have 2 times 6 is 12, plus 4 gets us 16 total electrons. Then, right, we need to figure out our kind of, where things are going. So if we think about the HONC rule, right, again, we're trying to put the one that can make the most bonds in the middle. So carbon, right, can make 4 bonds, whereas oxygen can only make 2. So since carbon can make 4 bonds, it goes in the middle. Okay. When we are doing this, what we call skeleton structure, it should be symmetrical. So you'll notice that I've put the oxygens on, opposite sides of the carbon rather than, putting one there and, maybe one on the top. We want to make it symmetrical. Molecules are typically symmetrical if they can be. So our next step is to attach the peripheral atoms to the central atom using, single bonds. Okay, so if we do that, we've got, now we've used up 4 of our electrons because each one is worth 2, right? Each bond is worth 2, and so we have 12 electrons left to play with. So 4 electrons used up, 12 electrons left. So now what we would do is we'd go and try and give everything an octet. So if we give oxygen an octet here, right, we've added 6 electrons to our structure. And so when we do that, oxygen has an octet, which is great. Carbon doesn't right now. Carbon's got 4 electrons, and the other oxygen has 2. And we only have 6 electrons left, right? We've used up 10 now, right? 4 in the bonds and 6 to the oxygen. And so there's only 6 left. So if we did that, right? So now we've run out of electrons. We've used all 16. There are 12 as lone pairs and 4 as bonding electrons. But, so even though the octet rule is satisfied for the oxygens, right now the octet rule is not satisfied for that carbon. That poor carbon only has 4 valence electrons. So this is not a good structure. So instead, right, our step 5, we need to take some electrons here. I'm going to play that again. We're going to take some of the electrons on the oxygen. Instead of having those electrons belonging to the oxygen, we're going to put them between the oxygen and the carbon. We're going to move them here, so that now, instead of them belonging to the oxygen, they will be shared with the carbon. So they're going to move right there. And now if we look at each one of the atoms, right, our octet rule is satisfied. So the oxygen on the left has 1, 2, 3, 4, 5, 6, 7, 8. The oxygen on the right has 1, 2, 3, 4, 5, 6, 7, 8. And the carbon in the middle has 1, 2, 3, 4, 5, 6, 7, 8, because each of those bonds are worth 2 electrons. So the octet rule is satisfied. Yay! This is a good structure. Let's try another. If you're feeling brave, you can pause the lecture and try and draw the structure of acetic acid. If you've seen Lewis structures before, try this one out. If not, you can just keep playing. All right, so acetic acid, you'll see that the way that it's written, right? Do you see that this whole CH3 thing right here? This usually means that there are 3 hydrogens on that carbon. And then you get to this next group, and the carbon has the oxygen and all these other things bonded to it. So here's what the structure looks like. Okay, and if we look, right, on each one of these, each carbon, this carbon has 1, 2, 3, 4, 5, 6, 7, 8. This carbon has 1, 2, 3, 4, 5, 6, 7, 8. Our oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen down here has 1, 2, 3, 4, 5, 6, 7, 8. And all of the hydrogens are only single bonded. So this is a good structure. This is a little bit of a trickier one, but we're going to get there. Okay, so when you're doing this, if you're like, wow, I didn't get that, go through and always add up how many electrons you have to work with, right? So we would have done 4 plus, there's 3 hydrogens and 1 each, plus 4 from that next carbon, 6 from each of the oxygens, and then 1 more from that hydrogen. So you've got 4, 7, 11, plus 12 is 23, plus 1 gets us 24 electrons that we need to play with. In our skeleton structure, I would have done, carbon, and like I told you, there were 3 hydrogens on that carbon. And then the other carbon looks like it has an oxygen and an alcohol group. So I would have done something like this. And then you would go through and try and bond it all with single bonds. And eventually you would realize that this would need to be double bonded. You will get better at drawing these Lewis structures as you go. Let's talk about drawing Lewis structures for polyatomic ions. So the procedure is the same as doing neutral molecules, except we're going to include the charge of that polyatomic ion in our electron count. If we have cations, right, positively charged ions, then we're going to take electrons away from our total. If we have polyatomic anions, then we are going to add electrons to our total. Okay, so this is what it looks like. If we were to write the Lewis structure for carbonate, so CO3 2-, again, our first step is to figure out, how many electrons do we have to play with? So 24 electrons, this is coming from 4 from the carbon. There are 3 oxygens that have 6 each, and then this 2- charge tells us that we have 2 extra electrons to play with. I know this sounds silly, but remember that electrons are negative. So if you have a 2-, that means you have 2 extra electrons, and you're going to add 2 to your total. Whereas if this was a 2+, you would have lost 2 electrons and subtract 2 from your total. I know it sounds silly. People make that mistake all the time. So when we add them up, so we have 4 coming from the carbon, 3 times 6 coming from the oxygen, plus 2 coming from the 2- charge, gets us a total of 24 electrons that we can play with. So our next step is to draw our skeleton structure. So again, thinking about the HONC rule, carbon is going to go in the middle because it can make the most bonds. Then we are going to attach all of our peripheral atoms to our central atom with a single bond. There we are. So we've used up 6 electrons so far, right? There are 2 in each of the bonds. So we have 18 remaining. So our next step would be, okay, let's go put electrons around each one of the atoms. So if we put some electrons here, now we have 12 left. We put some there, we have 6 left. We put some there, we don't have any left. And so all of the oxygens now have an octet, which is great, except for the fact that carbon doesn't. Carbon only has 6 electrons around it right now. Okay, so the octet rule is satisfied for all of the oxygens, but the octet rule is not satisfied for this carbon because it only has 6. So the way that we make that adjustment is kind of like what we did on carbon dioxide. Instead of having 2 of those electrons belong to one of the oxygen, we're going to donate them to the carbon. Okay, so we're going to move 2 of those electrons and we're going to make a double bond. So now, all of the oxygens, right, so carbon now has 8 valence electrons, right? 2 from each one of those 4 bonds, and all of the oxygens have 8 valence electrons as well. This is now a complete Lewis structure. And the way that we would actually finish this up, we would draw brackets around this whole thing and put the charge on the outside. So since this is a charged species, we put it in brackets and we put the 2- on the outside to show that this is a charged polyatomic. Now this would be a complete structure and we would be good to go. I do want to tell you, it doesn't matter which one of these oxygens we had picked to double bond to the carbon. You could, we picked the oxygen on the right, you could have picked the one on the left, you could have picked the bottom one. It doesn't matter. Any of those would have been acceptable ways to draw this particular Lewis structure, just as long as one of them gets double bonded and the other two do not. So again, if you're feeling brave, go ahead and try to draw the Lewis structure for the nitrate ion. So I would pause here and try and draw it. All right, so the first thing we want to do is count up our valence electrons. So nitrate has 5 from the nitrogen, 6 from each one of the 3 oxygens, and that minus charge tells us we get 1 extra electron to play with. So we have a total of 24 valence electrons. Then we're going to draw our skeleton structure. So we put the one that can make the most bonds in the middle. Again, thinking about our HONC rule, right? Nitrogen can make 3 bonds where oxygen can only make 2. So we'll put nitrogen in the middle here. And then we're going to connect the peripheral atoms to the central atom with a single bond. And so once we've done that, we had 24. If we subtract out 6, we've got 18 electrons left to use. So we could do this, right? We put, each one of those, the 18 electrons, we put them around the oxygens. So now, though, we have complete octets around all of the oxygens, but nitrogen only has 6. This is very similar to our last example. And so the way that we get around that and we fix that is that one of the oxygens will donate, right, will share that pair of electrons with the nitrogen. So it will move and go and share. So now nitrogen has a complete octet and all of our oxygens have a complete octet as well. Again though, since this is a charged species, we want to put it in brackets and put that negative on the outside. Again, it didn't matter which one of those oxygens I picked to double bond to the central atom, as long as one of them double bonds to the central atom and the other 2 are single bonded. And this is it. That is the end of the beginning of Lewis structures. So go ahead, get some practice. This corresponds to lecture worksheet chapter 9, pages 3 through 5. You have lots and lots and lots of Lewis structures to draw on those pages. I've provided a lot of practice problems for you so that you get really, really good at drawing Lewis structures. We're going to use Lewis structures for the remainder of the course. This is one of those kind of foundational pieces that I've talked about earlier, like when we got to stoichiometry and things like that, where you must understand how to draw Lewis structures in order to do a lot of other topics. So make sure you put in the practice now, get really, really good at them. They get kind of tricky fast. So do your practice now so that you're prepared for later.